Hi, welcome to Mathematics with Tom. I'm Tom, and today we're going to look at section 1.5 in our text, and it's about complex numbers. So we're going to take a look at complex numbers and find out what they are. So here we go. Let's see what one is, and then we're going to work with it. So a complex number has two parts. Has two parts. A real part and an imaginary part. Oh goodness gracious. Imaginary part. So usually we would we represent the complex numbers by capital C with this bar in the back, which is very similar to the real numbers. The real numbers when we represent them with this capital R with the extra bar on the back. And so what we would say is a Z, I'm going to use this little E symbol, E in Z. This little piece here is read as in. So Z is a complex number. So Z is a number in the complex numbers, and it has the form Z equals, our book is using X plus I Y. And it's not uncommon to see another complex number, we'll call it Z1, as written as A plus I B. So those are both common forms for complex numbers. And what we do is we say this. We say that the real part of Z would be the X, and the imaginary part, we write it capital IM, the arguments, that's Z. The imaginary part of Z is the part with the I on it, so it's just Y. Or, for example, if we look at the other number, the real part of Z1 would be A, and the imaginary part of Z1 would be the B. And not only that, here's what's also interesting is the X, the Y, the A, and even the B. All of those, that was a funny little symbol, all of those can just be any real number. So you can have a pi or a square root of 2. You can even have a 5 in there. Just any real number would go in the positions of the X, Y, A, or B. Now, here's how we represent a complex number. Oh, a little bit more. Here's what I want to show you is the complex conjugate. The complex conjugate of Z is, we represent the complex conjugate of a number with a bar over it. And what it means is you change the sign between the real and the imaginary components, or parts. So if Z is X plus IY, the complex conjugate is X minus IY. That's it. That's all you do. Now I want to show you something. Let's see how we add, subtract, multiply, and divide. Well, adding and subtracting are the same, just a minus 1. So let's add. So if I take Z and I add to it Z1, well, that's the Z is X plus IY, and Z1 we said is A plus I b, and we combine like terms. And combine like terms. So in this case, our like terms would be the imaginary components and the real components. So my like terms would be the x plus y, or x plus a, and my imaginary components are the y plus b. And that would be how you would add. It's multiplication and division that get more interesting. So let's take this, let's multiply. So if I take z plus, oops, not plus, multiplied. If I take z and I multiply it by z1, how does that work? Well, that's x plus iy times a plus ib. And now we distribute like you would expect. So if I multiply the x through, I get x times a plus I times xb. And then if I multiply now by the iy, I get plus iy a plus, then I get I squared. Oh, I pick up an I squared yb. And we'll deal with the, probably usually letters are in alphabetical order just for tidiness. Well, look at what happens though here. So if I combine these, I still I have an xa, and then I have plus, I have an I times, we'll call it bx plus ay. But look at what happens out here. This is where, if you recall, I squared is -1. So really, this becomes a real number now, yb. So my final answer is xa minus yb, or by, I guess, would probably be cleaner. That doesn't matter. Minus yb plus, that's my real component. There's my real part. Plus I have my imaginary component, which is the bx plus ay. Okay, now before we leave this screen, let's do one more bit of multiplication. Let's try this. What happens if I take z and I multiply it by its complex conjugate, z bar? Well, this is x plus iy being multiplied by x minus iy. Oh, look at this. This, I don't know if you remember, this is called a difference of squares. Difference of squares. Just like, for example, if you have a plus b times a minus b, there's a pattern, and the pattern is the middle components drop out. Well, let's try this here. So I'm going to have an x squared. Then I get a minus ixy. Then I'm going to pick up a plus ixy. And one more distribution, though, is going to give me a minus I squared y squared. Well, the middle two terms cancel. And what do I have now? I have an x squared. But minus, so I squared is -1. But I have minus a -1. That's a plus y squared. So look at what I did. I began with a difference of squares, but what did I end with? This is a sum of squares. Now you might say, well, why is that so important? And I'd like to show you on our next screen. So let's keep this result in mind. We'll go to our next screen. Here we go. Okay, so look at what we just said. We said that if you take z times its complex conjugate, that the result, which began as x plus iy times x minus iy, we just found out that the result is x squared plus y squared. Now, here's what's interesting. Remember when you first learned to factor, if I gave you a problem like x squared minus 9, well, you knew that factored into x plus 3 times x minus 3. But if I gave you a problem like x squared plus 9, well, you would say that this is prime, and so it can't be factored. But wait a minute. So it's really the correct or the full answers is prime in only the real numbers. But here's what's amazing is, but in the complex numbers, x squared plus 9, well, we just found out that would factor now. That's what this whole thing says. It factors into x plus 3i times x minus 3i. I've always found that so fascinating that this problem actually has an answer now. Okay, but we're just warming up. Let's try another one. What if I have a number like, so we looked at multiplication. Let's look at division. So here we go, division. So oops, if I could spell today, that would help. Division in complex numbers. So let's start with 1 divided by z. That's as simple as it gets, I would suspect. So this is 1 over x plus I y. Now the problem is if I asked you for the real part of 1 over z, or 1 divided by z, you can't identify it. You can in just the denominator, but not the whole number. In order to do this, we need to be able to write this so that we have a real number in the denominator. So how do we do that? Well, we use what we just learned. Let's multiply 1 over z by, we're going to multiply it by its complex conjugate, z bar over z bar. Well, remember, this is just 1. It's just a big 1, so we're only going to change its appearance, not its value. So I have 1 over x plus iy times x minus iy over x minus iy. Well, my numerator now becomes x minus iy over, and we already found out what z times z complement is. That's x squared plus y squared. And though it's so interesting about x squared plus y squared, and I should have set it up above also, is the product has no imaginary component. It's completely a real number. So now I have a completely real number in the denominator, and I have a complex numerator. Well, if you remember, you can undo fractions. We've spent our entire math process at this point trying to simplify or add our fractions. Well, what if we don't add or don't simplify? What if we unsimplify it? What if I think of this instead as, what if I think of this instead as x squared plus y squared is my common denominator? Let me give you an example, a better example. What we're going to do down there is, if, for example, if I gave you the number of 2/7 plus 3/7, you would normally rush to 5/7. But wait a minute, you don't have to. What if we started with 5/7 and then ended over there? That's exactly what we're going to do now. In other words, this is really the fraction, two fractions of x over x squared plus y squared plus minus, I'll write this right, plus I times y over x squared plus y squared. Whoa, now watch what we can write. So now, for example, we could say that the real part of 1 divided by z is x over x squared plus y squared. And we could also say that the imaginary part of 1 divided by z is minus y over x squared plus y squared. Okay. So that's a pretty good place to start. I think we're about warmed up. I think now we can begin to put all of this together. I'm going to go to a new screen so I have plenty of space to develop this concept. So I'm going to turn this screen off. Let's go to a new screen here. How about this one? And let's clear that. We don't need that. Okay. So now we can take a look at a complex number. So here we are. So we said that z is x plus I times y. Well, we're going to write z, so we're going to graph or represent. Let's do that. Represent z in rectangular coordinates. Rectangular coordinates. Or rectangular form, either is fine. I'll do that. Rectangular form sounds nicer. So what we do is graph there. Okay, so let's draw this graph. See what it's going to look like. So say I put my z right there, and we draw it usually as a not a ray, but a segment from the origin is usually the best way to think about it, and I'll show you why. So this is the point z equals x plus I, y. Now, how did I get there so fast? Let me show you. The horizontal axis represents the real component. The vertical axis represents the imaginary component. So if I put these numbers down here, here's x, and my imaginary component, that's y. There's my y. And so I've just graphed that value, or that's how I would represent z in its rectangular form. And also, now notice that we said z is represented as this line segment. Well, that segment has a length. We can see that. We can just see that. We can write, we're going to call this, we're going to write it a few different ways. The length of z. So the length of z, the length of z is, and often you'll see just an absolute value sign around z to represent its length, or sometimes you'll hear its or modulus. Fancy word for the length of z, and just so we don't even have to write that, or sometimes in our application we're going to be writing just lowercase r. So, well, r, look at it. R is just found using the Pythagorean theorem. It's the square root of the x value, the real piece, plus the imaginary piece. X squared plus y squared. So this. Now we've got r, the length of z, and that's x squared, square root of x squared plus y squared. Now we've got z in rectangular form. That's really all there is to it. But we're going to do another representation. So now let's do this. Represent z in polar form. Represent z in polar form. All right. Well, then that means that this modulus, it sweeps out some angle. Let's call this angle, let's call this angle here theta. So that's what's very common. We could use an alpha or even an omega t, but we're going to start with a theta. Okay. Then, oh yes, look at this. Well, notice what we've got. We've got a few relationships. Remember that the cosine, so if I said the cosine of theta is the adjacent side over the hypotenuse. Well, our adjacent side is x, and our hypotenuse is r. So here's my adjacent side, and we've got r in there, and there it is. So cosine of theta is x over r, and I'm also, so that I could just multiply both sides by r, so I could also rewrite that as x is equal to r times the cosine of theta. Okay, and let's do this one more. We'll do this in a slightly different color here to kind of keep track. And also remember that the sine, so that the sine of theta is the opposite side. Well, the opposite side, that's this one over here, that is y. So it's the opposite side, y, divided by its hypotenuse, which is r. If I multiply both sides by r, I could say that y is, y is equal to r times the sine of theta. Okay, think we're looking pretty good here. Now, let's continue. Oh, this is beautiful how this works. Watch. What did we say? We said that z is equal to x plus I times y. Well, wait a minute. What did we just say x was? Well, down here in the bottom left, we said that x is equal to, I'll put it in parentheses as we substitute this in, is equal to r times the cosine of theta. Plus, we have an I times y. Well, down in the bottom left, we said that y is r times the sine theta. Let's do that. Obviously, we have a greatest common factor of r, so let's factor out our r. So I'm going to write this as z equals r times, parentheses, I have a cosine of theta, plus I have an I times the sine of theta. Oh my goodness. Do you remember this? This was what we said when our differential equations, we found that cosine of theta plus I times the sine of theta is the exact same thing as e to the I theta. We used t in our differential equation, but now we're just going to use theta. It's the same thing. And look at that. So in other words, we can represent the polar form of a complex number as an exponential. And we're going to use that fact now. And let's just see how this works. Well, it gives us a few advantages. For example, let's try this. If I wanted to take z times z1, and we said earlier that was a plus bi. Well, z we just said is r e to the I theta. Well, z1 would have a different modulus, r1, and it'd be e to the I, I'm making these up, but it's just as long as they're different, I alpha. Well, if I want to multiply those, then this becomes r times r1, and then you add, all you have to do is just add the exponents. So this becomes e to the I, I'm going to factor it out the I, it just becomes theta plus alpha. Wow, that makes multiplying complex numbers so simple. Watch this. What if we take a look at z divided by z1? Now remember, in there previously when we divided numbers, what we had to multiply by complex conjugates. Well, look at what this says. This says that r e the I theta divided by r1 e to the I alpha. Well, now I just have a number. I just have the modulus, the length of the first modulus divided by the length of the second modulus. And then we just have an exponential, the bases match, so we can just write this as e to the I, and now we just subtract the exponents, theta minus alpha. And I have to admit, that's a lot easier for the sake of application. Pretty easy. Now, I think that at this point, sometimes we get a little confused with all these letters. So let's actually try an example. So here we go. We're going to try an example. Come to a new screen. Let's try this. We're going to use a new z. So z is equal to 4 plus 3i. Okay, I'm going to graph this. So if I went 1, so here's my real component. There's my imaginary component. 1, 2, 3, 4. 1, 2, 3. So if I went over 4 and then up 3, looks like I would land right there. And there is my angle. Oh, so z, this is z is 4 plus 3i. And let's find the length of z. So z is going to be the square root of the two parts. Well, the first part is 4, so we square that. And the second part is a 3, square that. Well, that works out to be the 16 plus 9. That's 25. Take the square root and we get 5. So our modulus is 5. And remember, modulus can also be written as the length of z, like that. And now let's write this in polar form. So what I want to do now is we need our theta. We're going to find out what theta is in here. Okay, so what do? Well, what do is we know this. We know that theta, oh, watch this. The tangent, this is what we do know, that we know that the tangent of theta is equal to the opposite. Well, the opposite is 3 over the adjacent, which is 4. So we can say the tangent of theta is 3/4, or we can say that theta is the arctangent of 3/4. And depending on the book, some people write it also as tangent inverse of 3/4. Either of those are absolutely just fine. And that is how we work with complex numbers. And I hope that helps. Thanks for watching.